So I have here a cone, so I'm going to hold at this height and release. We're going to record the time that it takes for the cone to fall and also the distance that it falls, and we'll use this information to estimate the air resistance force acting on the cone. We'll then use this figure to make a prediction about a slightly heavier cone. So here goes. The distance fallen by the cone is 203 centimetres. The mass of the cone is 6 grams. I'm going to start by using the equation s equals ut plus a half at squared to find the acceleration of the cone. We know that s is equal to 2.03. U will be 0, so this term will disappear, and that will be equal to half times a times 1.1 squared. Solving this equation gives me a equals 3.36 meters per second squared. The diagram shows the forces acting on the cone, the weight acting downwards, and what I'm assuming is a constant air resistance force acting upwards. The resultant force on the cone will be downwards, and the resultant force will be 0.006 G minus A. That will be equal to the mass times the acceleration. The mass is 0.006 and the acceleration we have calculated as 3.36. Solving this equation gives a value for A of 0.039 newtons. I'm now going to repeat the experiment by changing the mass of the cone. The actual cone is going to stay the same, but I'm going to put a lump of blue tack into the bottom of the cone like that, so that we create a heavier cone. With a lump of blue tack placed in the bottom of the cone, the mass now becomes 10 grams. The diagram shows the forces acting on the heavier cone. We're assuming a constant air resistance force which has the same magnitude as we determined in the previous experiment. The weight will now be 0.01 G. So the resultant force on the heavier cone will be 0.01 G minus 0.039, and that will be equal to the mass times the acceleration. The mass is 0.01 and the acceleration A is what we're trying to find. Solving this equation gives A equal to 5.9 meters per second squared. We can now use S equals ut plus a half at squared to find the time that we would expect this cone to take to fall. S will still be 2.03. Again, ut will be 0, and we will have a half times 5.9 t squared. Solving this equation gives t equal to 0.8 seconds. Now I will drop the cone containing the lump of blue tack. We've now done the experiment and seen that the cone took a little longer to fall than we expected. This is actually very reasonable, because if we consider the air resistance force, the surface area of the cone is still the same and that won't affect the air resistance, but because the cone does move a little faster, we would expect this value to be a little bigger for the heavier cone. But nevertheless, this is quite a reasonable prediction.